Hello, welcome to your CS 1332 Exam 2 review session. We're here live from the TA Lab to bring you some quality review content. I'm Jacob, I'm your head TA, and before we begin today, just want to go over some brief things that you need to know before we get started. First of all, thank you to everyone who filled out that Google form. It gave us tons of great questions to start off, and we're going to start off today's review session by going over a lot of these questions that are already submitted in order to make sure that we can get good answers to those. However, we're not just using those questions. Feel free the entire duration of this review session to submit more questions in through the YouTube chat. I'll be monitoring it constantly to see more questions, make sure we can get them included in today's review session. If you ask short questions that are really easily answerable over just a quick message, I'll probably just respond to you in the chat. However, don't worry, for people that aren't able to watch this live, I will include those questions in an accompanying document that gets released with the stream VOD. If you ask a question that we already answered previously in the review session, I'll let you know that we've already answered it so that you know you'll be able to find it if you go back and watch the VOD, but we probably won't go back over it again unless we get through a bunch of our other questions in order to cover as much different content as possible. With that, bring it over to our wonderful TA Yoon, who will be going over our first question. We'll be swapping out TAs throughout the review session so people can get a break, but that's enough from me, and now on to the review session.
Hey, what's up, YouTube? Okay, so the first thing that we're going to go over are properties of sorting algorithms. So the first thing, or the first property that I want to go over is stability. So what stability means is that relative ordering of duplicate elements in the array remains the same after the sorting takes place. So for example, if I have an array like 2, 1, 3, 5, and 2. So if I have an array like this, you see that I have two 2s, so the black 2 in the front and the purple 2 at the back. After the sorting takes place, the black 2 should remain before the purple 2. So the relative ordering of duplicates should remain the same. So if I sort this, 2, 3, 5. So you can see that the black 2 is still before still comes before the purple 2. Okay, so that's stability. The next property is adaptiveness. Oh, really? Yeah, I want to just write purple. So adaptiveness. So the way I like to think about adaptive algorithms is that it somehow takes advantage of the fact that the array might already be partially sorted to terminate early. So I'm going to just write that down real quick. Actually, it doesn't have to be partial. So for example, if I have an array like this, so you see that this array is not completely sorted, but it is already partially sorted. So 1, 2, 3, 2, 5, and only 2 is out of place. An adaptive algorithm can take advantage of that and terminate early. Okay. The next property is going to be in out of place. So what in out of place is, if an algorithm is in place, it's going to sort just within the array that was given. And if it's out of place, it's going to move the elements temporarily into an external data structure. So a good example of in-place algorithm is bubble sort, and quick sort as an example. And for out of place, you have merge sort and radix. Because both algorithms move the elements into an external data structure that you create outside of the array. Okay. Do we have any questions so far? Yep. Okay, so a lot of people probably want this, so I'm just going to get rid of this. But I'm going to talk about so sorting scenarios, which sorting algorithms are better in which scenarios. And generally speaking, we're going to look at these properties, so stability, adaptability, and in out of place to see which algorithms are going to be better. So for example, so let's say the question, so what I like to do is sort of look for these keywords when reading the question. And the keyword might be something like, let's say it says you're in a memory constrained environment. Okay, so if you have a memory constrained environment, then you can probably get rid of algorithms that are out of place because they're going to take more space. They're going to use more space. Another keyword might be something like speed or consistent speed. So if you want consistent speed, then you probably want to get rid of algorithms that have a worse case than the average case. So a good example of that is quicksort. Because quicksort on average is O of n log n, which is pretty fast. But the worst case is O of n squared. Right? So quicksort is not going to give you as consistent of a speed as, say, merge sort. Another thing that you might look out for is, let's say the question says you have an array whose size is relatively small. So pair to digit. So let's say you have an array of size 50, but the numbers are really big. So you have numbers that have like 100 or maybe even like 1,000 digits. Then you can say, you can rule out LSD Radix sort, right? Because LSD Radix sort depends on the number of digits to sort, right? So you may have something like that. As for stability, so imagine that you have imagine the school has an array of students. That are already sorted by names, last names. But let's say the school wants to sort this array again by exam scores, some exam score, and within the same exam score, they want the names to be sorted. So if you have, if say Jacob got an 80, and let's say Garrett also got an 80 on the exam. So when I sort this array, this already sorted array by exam score, I would want, because they were already sorted by name, I would want Garrett to still come before Jacob. So within the same exam score, I want the names to be sorted. So if I want that, then I would want a stable sorting algorithm. Okay. Do we have any questions so far? No? Okay. Cool. All right. Well, that's it for sorting scenario.
All right, next up, I think we're going to talk about handling 2-4 tree overflow and underflow. We'll be right back with that.
Hello, 1332. Okay, now we're going to go over 2-4 trees and specifically how to handle overflow and underflow. Okay, so first let's handle overflow. It's a little bit easier. It's important to note that this only happens in adding. And there's really only one way to solve overflow, which allows us to have a really easy example. Okay, so let's make our 2-4 tree. And all right, so here's our initial 2-4 tree. We can see that it is a valid 2-4 tree, right? Because we have only nodes with 1 to 3 data elements, right? And every node that has a data element in it has either 0, in the case of these leaf nodes, or m plus 1 children, right? Where this would be m being 1 and the plus 1 being 2 children, okay? Now, let's do the operation add 18. We would traverse through this tree just like it was an AVL or BST, right, where we come in at the root and we'll see that the value 18 is less than this number, so we will go to the left, and then we will search through here to find the appropriate spot to insert our data. But if you notice, we now have 4 data elements in this node, and our max is 3. We have a max of 3 data elements per node. So now we will have to promote one of these data elements up to the parent, and this is how we handle overflow. So the easiest way to do that, you will be told to promote either the second or the third element, and this would be told to you. In this case, we're going to promote the third element, and watch what happens. We'll move 12 up with 20 beside it, right? And hopefully you can notice that now we have 2 data elements, right? So to satisfy this, m data is m plus 1 children. To satisfy this requirement, we now have to split this node. And luckily, it's very easy to see where you split it, right? Right where the element that you promoted, that's exactly where the split will be. And if you'll notice, this node will always be between the element you just promoted and the initial data in the parent node. And this node will always have data less than the data you just promoted. So this will be a far left marker, and this will be a central marker. And now we've done one simple promotion, and we've solved our overflow. Okay? It is possible to have this continue, in which overflow will keep propagating up the tree. In that case, you would just create a new node, or a new root node. And we can, I don't have an example of that. Do we want to just, for overflow making a new root node? How do you guys feel? Do you want to see an example of overflow creating a new root node, or do we understand how that happens?
Someone asked about doing it for doing a specific example, so I'll check so I can do that example.
Okay. So did we get any yes, no's on? Okay, cool. All right, yeah, so we will go back to that if necessary. But essentially, for all of those who are curious, if you promote from here to here, but then this still necessitates promotion, you literally just make a new root node. It's pretty simple. So this is all we really need to go over for overflow. It's a very, very easy solution to fix in 2-4 trees. Now, let's look at underflow, which is only in removing. And I think for this one, it's very important to... Okay, so we are going to go back to that new root for overflow then at the end. But... Okay, cool. We'll do that then. But I think it's very important when you're doing the removes, you really want to have your node properties continuously in mind, right? And these properties are 1 to 3 data, m data necessitates 0 children or m plus 1 children. Okay? And this is going to become very, very crucial here, because when we're doing when we're handling underflow in 2-4 trees, I find that students see it particularly helpful to almost view these things in screenshots, right? Because there will be cases in which you attempt to solve the underflow, and you will do an operation, right? But this operation won't solve the underflow by itself, right? So, starting with that, let's look at the 2 operations we can do. We have the first one, transfer, and the second, fusion. We will always try transfer first. right? Okay. So now, and let's look at an example as to why this is the case. So we're going to have a pretty big tree here. It's kind of complex. Ooh, and then off the 45. Okay, this is our tree that will stay with us for quite some time. I highly recommend that when you're working through these problems and going back through this video, that you take a screenshot of this initial tree here. I think it'll come very much in handy for you, because as I do operations, we're going to have to manipulate this tree. So the first thing we're going to do is remove 10. And this is an example, and we shall see, right, of a very easy and simple 2-4 tree remove. So we'll come in and we'll remove 10, traverse through the tree just like we would in a BST, right? And then now we get underflow right here in this node. Now this is very important. A lot of people forget this. Whenever this happens, whenever you get underflow in an internal node, you're always going to replace it with the predecessor or successor, okay? And we just removed 10, so let's use the successor method, which would have us grabbing 18. And what that will do is pull 18 up and move the underflow into this leaf node. It is very important to realize that because we are always going to be using a predecessor or successor function when we end up with underflow in an internal node, at least initially, right, that underflow will always start in a leaf node. Okay, so you definitely should be starting with underflow in something like this, right? Now, we get to actually try to solve the underflow in this tree. And the first thing we're going to try, as we said before, is transfer. Now, you guys should remember that transfer is possible when a directly adjacent sibling has more than one data, okay? And if we look at this node, this is our node in question, we have a directly adjacent sibling with with more than one data. And I want to be very explicitly clear on this. We're going to change this tree slightly. We'll go back to here. I know that this isn't a valid tree. We'll just put something there and then like 2 things here. So I want you to notice that in this case, right, we have underflow in this node. There is no data in this node, right? And we have a sibling with more than one data, but it is not directly adjacent. Now this is the node we're looking at. It is not directly adjacent. So in this case, we cannot do transfer. This is what I mean when I say an immediate sibling with more than one data. Let's put this back. Okay, and this was our initial tree, right? So we do have a sibling with more than one data, so we can do a transfer. And a transfer is very easily, we're going to pull data from our parent. And notice that we're always going to pull data from the parent when we're doing 2-4 tree operations to solve underflow. And then we're going to take the nearest data in that adjacent sibling and promote it up to the parent. So it's almost like a rotation. 5 goes up, or so 18 goes down, and 5 goes up. And now if we look at our node properties, right, we've got all of these nodes have at least one data, which is good. This node has 2 data and 3 children, so we have completely solved this tree. A single transfer operation solved this 2-4 tree. It is extremely important to note, and this is why we always do transfer first, that if we can do transfer, it will immediately solve underflow. Okay? And we're going to show an example in which we'll have to use fusion and it doesn't immediately solve the problem. But first, I do want to show you a very simple fusion. So, now, let's do remove 31. All right, so we'll recurse through the tree, and we'll find 31. We'll remove it, and instantly we have our underflow in our leaf node. Now we check to see if we can do transfer. Always think of that. Always check to do transfer. We do not have an adjacent sibling with more than one data, so we'll have to do a fusion. Now a fusion happens when we'll pull data down, the closest data down from the parent element. So we'll pull 20 down. And now, if you notice, to satisfy these properties, we have a node with one data, right? Which means that it should have two children. Well, a fusion will fuse the node that was in underflow, which was this node here, with its adjacent sibling, just like so. And now, if we check our properties, we have one data, two children, right? And all nodes are valid in terms of like they have at least one data in them and they don't have more than three. So fusion solved this in one step. And it's a particularly easy step. Students like to do this. But now I want to show you why we prefer transfer to fusion. So this time, let's remove 49. Right? When we remove 49, we'll recurse through the tree. We get underflow right here. Again, we check if we can do transfer. It's not possible, unfortunately. So we'll do a fusion in which we pull down data from the parent and we fuse it with its adjacent sibling. Cool. But now notice this. This parent had only one data in it. So now that we've pulled from the parent and there was only one data there, we've propagated underflow up the tree. This is bad. This is like, it's necessary here, but this is something we don't want to do, and it can only happen in fusion. So now, we are in the case where we must check to see if we can do transfer again, right? We look, we don't have a sibling with more than one data, so we're going to have to do fusion again. 36 will come down, and we'll fuse. So and our underflow will go all the way up to the root, and we'll fuse this node. It's a very big node. Now, this is the case where underflow is propagated all the way up to the root of the tree, right? And in this case, we just delete this root and set this child, its single child, as the new root, right? So this is what our tree currently looks like. Right? And this is an example of fusion solving the problem but having to be done twice, right? And that's how we had that propagation up the tree. I really want to point out to students, because we're going to see this in the next example of how transfer can fix it, and it looks a little wonky and funny, but students will see that we just propagated underflow up, that we got rid of the root, and it looks like, cool, that's a great solution. But imagine that this tree was a very small subtree of a much larger tree. To continually propagate underflow upward could have a lot of operational cost in fixing this 2-4 tree, and that's why we don't want to do it, right? So we're always going to prefer transfer first, and let's see an example in which transfer is going to solve our problem, but in a more complicated environment. So we're going to actually start with a new tree here to completely illustrate this. This is it's a fusion that propagates underflow upward, and then it will be followed by a transfer to solve it. But I want to show you yeah, this is fine. Okay, so we're going to actually, I can just do the one on the reality check because I think you guys have already seen that and hopefully have thought with it. So let's look at this. I think this does exactly what I want. 597, 11, 389, 549. Big nodes here. 806. 680. And 953. And then this guy's got a whole bunch of kiddos. Do you know what this first number was? 7? Cool. 7, 101, 188. 220. And right over here, we'll have 593. Okay, guys, this got a little crunched in. I just want to be very explicit in saying that this is the farmost right child of this node. So this node has 3 data elements, right? We expect it to have 4 children. 1, 2, 3, 4, right? It is not connected to this node over here. All right? So the operation we're going to look at is removing 680. Right? We'll recurse through the tree. We'll get down to 680, pop this bad boy out, and we've got our underflow in our leaf node as we expect. We look to see if we can do transfer, right? We only have 1 data here. So we're going to have to do fusion, pulling data down from the parent, fusing these 2 nodes, and consequently propagating our underflow upward because, again, we only had 1 data element in the parent, right? So when we propagated it upwards, we're guaranteed to now have underflow in this case. So now we're going to see something different. In the last example, we were forced to do a fusion again, which continued to propagate underflow up the tree. We don't want this. It's no bueno. So we are going to now we're going to try to do fusion, sorry, not fusion, try to do transfer. And if we look, we have an adjacent sibling with more than 1 data element, right? So let's do this transfer. And we're going to see something very interesting here. We'll pull from the parent. So 597 is going to come in here, right? 549 is going to get pulled up into the root of the tree. But now notice something, okay? Before, when we did transfer, in the easy example, it was happening in leaf nodes. And leaf nodes get the 0 children case, right? They have M data, but they have no children, right? If you have children, then you must have M plus 1 children, where we just transferred a data element from here to here. So this had 3 data elements and corresponding 4 children. Now it has 2 data elements, and we now have 1 more child. This is probably the hardest example for most students, and I want to just really easily, because it's actually a very easy fix. We just move this the child node that's closest to the node that was originally trying to be solved, right? The one that got the transfer and data pulled down from the parent. In this case, it's the farmost right node, and we'll reattach it here. So now if we notice, 2 data elements, 1, 2, 3 children, 1 data element, 1, 2 children, because this node was just fused. And transfer instantly stopped the underflow from propagating up. We now have a satisfied 2-4 tree, and we're good to go. I think this encapsulates every single underflow example that you can come across. I really, really want to hammer to people the way that I do this, because you can see that multiple steps will happen, right? Every time you move underflow anywhere, just kind of picture it like it's a brand new problem, right? If you first remove something and it's in an internal node, then you're going to use a predecessor or successor, and you're always going to end up with underflow in the leaf. But if the underflow propagates upward, don't try to think, oh, I have to do a fusion, and then I have to do a fusion, or I have to do a fusion, and then I have to do a transfer. Really just say, hey, I did a fusion. Now I'm in this entirely new environment, right? I've got underflow at some node like this one was, right, in my tree. let me ask myself the same question I always do. Can I do transfer? If so, let me do that. If I have to do fusion, I'll do that, right? Okay, so I think we wanted to see one example of overflow. Okay, so this is also another example from your reality checks. And and 186. I make this guy kind of long because he's big. 643. And 762. All right. So now we're going to do the operation. All right. So we're back in the overflow case. These are no longer appropriate. I'm good. I'm back on? Cool. Sorry for the brief technical difficulties. We're back in the case where we're looking at overflow, right? And we're doing adding. This is going to show you an example of overflow propagating all the way through the tree. So this is from the reality check. It was a tree I was copying down before we went off. Nothing's changed on it. Now we're going to do the operation add 670. Right? So we'll recurse through our tree. We'll come here. We'll realize that, so greater than, between these two, we're going to come down here. And 670 ends up right 70 and 693. Rut row, we have more than 3 data elements in our bottommost node, right? That means that we're going to have to promote something to solve this overflow. And in this case, we're going to, and this will be told to you as before, so we're going to promote the second element. So we'll look at 663, and we will promote this up to the parent. Right? But, rut row, we're kind of in the same problem again, right? We now have more than 3 data elements. Sorry, I have to split this too. Don't forget that. So we promote, and these will be a right reference from there, with this being a left reference here. Okay? So now we have 4 data elements, which is more than our tree, or more than our nodes are allowed to have, and we must promote again. So we're again going to pick, and it's important to be consistent, promote the second element. 391 will go up into its own new node. Yay! And we'll make the references as such, kind of like right along the split, right? So now if you look, 1 data element, 2 children, 1 data element, 2 children, 2 data elements, 1, 2, 3 children. And our tree is satisfied, right? This is the example of where overflow propagated all the way through the tree to necessitate you creating a new root, right? Which is probably the longest and hardest overflow example you can do. But as you can see, it's pretty easy and straightforward. Do we have any other questions regarding 2-4 trees? So there's a little bit of a delay, which is why we pause. Yeah. Anything? Okay, so
All right.
you guys are satisfied on 2 4 trees. I think next I am passing it off to Landon. So I pass it off to you, who pass it off to Landon, who is hopefully not going to pass it off to you guys, or you're in trouble. No, we're kidding. He's going to do the build heap diagram for you. So are we going to go to a pause screen? And sure. All right.
walk you through some min-heap diagramming. I chose min-heap instead of max-heap, doesn't matter, it's the same thing. The only thing that's going to change between a min and a max-heap is the shape property, or sorry, the order property, right? Where every single element in a min-heap, the parent of a min-heap has to be smaller than its two children, right? For a min-heap, and then for a max-heap, the parent has to be larger than its two children, right? That means that the root in a min-heap is guaranteed to be the minimum element, and the root in a max-heap is guaranteed to be the maximum element, right? So that's the order property. And then the shape property just refers to basically that the tree is full, right? That means it's filled from the top level down. Every single level is complete, or every single level is, sorry, it's complete, not full, my bad. It's complete, which means that every single level except for the leaf level is filled, and the leaf level is filled from left to right, right? So you can see that how everything on this level is complete, complete. This one's complete. This one's complete, and then here, the only node that exists over here is filled from left to the right. So when we're doing build heap, right, what we're really doing is we're down heaping from index. We're going to be doing down heap from size divided by 2. Right, and the reason that we down heap from size divided by 2, and then we just decrement all the way through to the root. Right, and the reason we do that, do size divided by 2, is because size divided by 2 is the first index, the first index in the array that is guaranteed to have children. Right, and I'll show you over here, this is how the heap is backed with an array. I'm just going to draw and diagram an actual kind of tree structure. We just use this because it's very easy to get between parents and children, so it makes sense to use an array. Right, and that formula that I'm going to use to get between a parent and the child is just, if I'm at the child and I want to get to the parent, I just take I divided by 2. Right, and because of how Java handles integers, it's just going to floor whatever that number is. So whether it's the left child or the right child, that's just going to result in the parent index. There's no other fancy business that goes on. And that's conveniently because we null out index 0, right? There's nothing there. So I'm going to go ahead and get started, right? Size is 8, so that means I'm going to start down heaping at index 4, right? So I'm going to start right here at index 4, right? Index 4 is 45, right? So I start right here. This makes sense because this is the deepest node in the tree that has a child, right? So I start at 45, and I'm doing a min heap, so I'm going to say, okay, out of its children, first I need to determine what is the min child. There's only one child, so that's super easy, it's 25. And then I just check, okay, is 25 greater than its parent, 45? It is, right? So I'm going to swap the 2. Put index 8 above heap. Oh, I can do that. Right? My bad, guys. 45. Alright, cool. So, right, then I'm down heap, and now I go to the leaf node over here, and then I say, okay, I'm at a leaf node, I can't down heap anymore, so that down heap is done, right? Then I decrement, right? I was down heaping at index 4, now I just down heap at index 3, right? So now I'm focusing on this. I'm going to down heap over here, right? So I'm going to go to index 10 in the tree, right over here, and then I say, okay, out of these two children, which is the min is 5, right? 5 is less than 15. And then I check, okay, now that I know the min child, is 5 less than its parent, 10? 5 is less than its parent's 10, so I'm going to swap the 2. Alright, this is 10. This will be 5. Nice. Over here. Alright, so then I go over here and I would continue down heaping down the tree, and then I determine that, yeah, 10 is at the leaf node, or is that there's nothing below 10, so I can't down heap any further. That down heap terminates, right? Alright, so now I'm going to decrement again. Right, I'm going to decrement and I'm going to down heap at index 2, which is 20. Right. What? Has anyone been able to hear me the entire time? I talk loud. Hopefully it was loud enough.
Just keep going.
Okay. Well, let him know if you haven't been able to hear me. So anyways, go on, right? So now I'm going to down heap at index 2. Right, I'm going to down heap at index 2. A little bit down. Okay. I'm going to down heap at index 2. And then what happens is, that goes over here to 20. Right? I need to determine the min child of 20. This is between 25 and 30. 25 is less than 30, so 25 is the min. And then I say, okay, is 25 less than its parent, 20? It's not, right? So the down heap fails automatically, right? It terminates, and then we're done. Right, now we just have one more thing to do. We decrement once more, and we're going to down heap at the root at 70, right? So now I'm at 70. I need to determine, okay, what is the min child between 5 and 20? Clearly it's 5, and then I'm going to determine, okay, is 5 less than its parent, 70? It indeed is. Really? Okay. I talk loud, so it's not a problem. That is funny, though. Okay. So I'm going to swap these two, 5 and 70. And now the down heap continues, right? Because now I need to check, okay, is this subtree also a valid min heap? Right now it's not. Right, so now I need to do the same thing. I keep on down heaping. I say, okay, what is the min child between 15 and 10? It's 10. And I say, okay, 10, the minimum element in this subtree, or out of its children, is it smaller than its parent? It indeed is. So I'm going to swap 70 and 10. Right? All right, and we're getting close to done. 70, 10. Right.
I just down heap at index 1. That means I'm done, right? There's nowhere else to index or to down heap from, right? I can't down heap on null, clearly. Right, and so now I know in this scenario, now I can redraw the array. I can redraw the array now in valid min heap form. 1, 2, 3, 4, 5, way short. Okay, I'm going to divide this one in half. 5, 6, 7, 8. I'm not very good at drawing these things. Anyways, obviously the first element's null, and we can repopulate this just as we were doing before, right? Hopefully this is clear that these are indices and this is the bottom of the tree. I'll probably try and make that a little bit more clear, right? This is the tree. Right, okay, so then I say, okay, well, what's at the root? It goes at index 1, right? So I go 5. 5's left child is 20. 5's right child is 10. 20's left child is 25. 20's right child is 30. 10's left child is 15. 10's right child is 70. And 25's left child is 45. Right? And so now in array form, it's difficult to tell just by eyeballing as a human if it's a valid min heap, but then we can check and we can start from the bottom and we can say, and really that's exactly what we've done is we've said, okay, starting from the very bottom, is this a valid min heap? Think about this subarray or this subtree right here, right? Yeah, and it is. It follows both the properties. It follows both order and shape. Then I extend this over to this subtree over here, 10, 15, and 70. That's also fine. I extend this over here all the way to this one, all the way over here. I say, okay, is this a valid min heap? It is. And then I go all the way back up to the root. I say, is 5 the minimum element? Yes, it is. Both of its children are smaller than it, and we already determined that those subtrees over there were valid min heaps. So we're done, right? Really the main thing that you need to do here is just understand that you're just down heaping from size over 2, and then you go from down heap from size over 2 to 1, right? I can draw that out a little bit clearer if you guys want that. But what we're doing is essentially when we're given any heap, all we need to do to validate that heap, when we perform the build heap operation, is just down heap from size divided by 2 all the way to 1. Right? And once we do that, if we do that correctly, it'll be a valid min heap. Same thing applies for max heap. All you're doing is just the condition you're checking. You're finding the max child in that case instead, and then you're comparing that to see if the child is larger than its parent. If so, then you swap. All the other termination conditions are the same. So unless there are any questions, I'm going to move on to...
Can you put the, so you have the relation between like parent, right?
Yeah, you want me to do child? Yeah. So if I'm at a parent to left child, right? That would be I times 2, and then parent to right child times 2, or sorry, I times 2 plus 1. Right? Hopefully that's clear. I kind of drew it at an upward angle. But, okay, anyways, and this is a 1. All right, if there are any more questions, let me know. If not, I'm going to move on. I think I gave it a decent amount of time because I had to write down the thing. Yeah, so I'll just go, just put me on intermission and then I'll go and
play again. Hopefully, let me know if I need to hold the mic, but it's more comfortable for me to just like go like this. Anyways, we're gonna do recursive coding help, right? I know there's like sometimes a little bit scary on the exam is like the coding questions, especially if there's recursion involved. But this is kind of like my 3-step process to being able to like tackle these problems. So the first thing you do when you read the question is understand like what are we asking for? And that seems so basic and so, you know, intuitive, but really I want you to think about what kind of properties are we looking for in the what we're going to return, and then I want to know what kind of traversal we're going to do. What portion of the tree are we going to be going through? Just one side of the tree, the entire tree, you know, only nodes that have a certain condition, stuff like that, right? So part 2 is there a fairly painless way to do it in code, right? We give you a coding question on the test. We don't want you to, it's not going to be, you know, the length of your remove method in your AVL, right? We're going to want you to be able to do it probably decently concisely, right? Because that's going to make it easier for us to grade. And we want to know if you know how to do it, right? And if you know how to do it correctly, it'll probably take you not a whole ton of lines, right? And then that goes into diagramming on a micro and macro scale, and then thinking about some edge cases. Right? Then the next thing you're going to do after that is we're going to translate that into code. Right? So the example of doing for you guys today, it's from practice test 2, 2018, question 7. Right? So you guys can follow along there if you want. And the question is basically it says, in a whole lot more words, it says count the number of even nodes in the tree. Right? So then when I think about it, I go straight for part 1. Right? I'm going to be the student. I'm going to act like this is the first time I've seen the question. Right? I'm going to say, okay, what are they asking for? Right, and then immediately I'm going to underline some of the important things, right? I know count, right? As soon as I see the word count, I know that probably I'm going to be counting something, and that maybe I should think about having my recursive method return an int. Maybe it's another question it's asking for, you know, to build a string or something like that, right? So I immediately identify this as key bit of information. I'm going to count the number, okay, that's pretty obvious, and then I'm going to say, okay, even nodes. Only even nodes, right? And we've defined an even node to be any node whose data is considered even. Right? And then I say in the tree. And in the tree is another important word, or another phrase, because that tells me that I care about the entire tree. I don't care about just traversing to the left or the right, one subtree or whatever. I care about the entire tree. Right? And then I want to look at the example. I want to look at the example that I'm given and see, okay, is there any other information that I can learn from it? Right? And this is the example, very basic, and it's going to return 3 when even count is called on it. Right? So anyways, and that makes sense, right? 1, 2, 3. So then I'm going to think about it, now I'm going to go to part 2. Right, I'm going to think about it on a micro scale and then on a macro scale. First I'm going to think about, okay, I have an entire tree, I have a huge massive tree, right? Counting the number of even nodes may sound intimidating, right? But let's think about a case where we know is actually what's going to happen, right? Let's think about a case like this, right, where I'm going to say, okay, 4, 5, and then 3, right? Think about this if this is our entire tree. Right? Actually, I'm going to make this a 6. Right? I'm going to say, okay, an even count, what would even count return in this tree? Right? Clearly, it would return 2 for the 4 and the 6. But then I would think about, okay, how did I arrive at that answer? Right? And really what I did is I said, okay, I got to 2 because I thought of, okay, how many even nodes are in the left part of the subtree? How many even nodes are in the right part of the subtree? And how many even nodes are in the current node I'm looking at? The current node is in the root, right? And really, if I can somehow find that out, if I can find out how many are in the left, how many are in the right, and if the current node I'm at is even, well, that's all the information I need. There's nothing really else I need to do, right? So I kind of have a formula in my head. I'm going to say, okay, left. Oops, I'm going to write it slightly more to the out of the way so that it's not going to interfere with anything else, right? I'm going to say left. Plus right, plus is even, or plus root if this is even, right? And then that's my answer, right? If I can find out these 3 bits of information, I'm done. I'm going to solve the problem. Right, so now let's think about the things we've learned, right? Now I'm going to translate this into code, right? So then I say, okay, so I knew that return type of this method needs to be an int, right, a recursive helper method. And then I think I'll call it even h, something like that. That doesn't matter. Even h, just because I don't want to write out a long name in my helper. Then I'm going to think about, okay, what kind of parameters do I want? What kind of parameters do I want for my helper method, right? I'm going to think, okay, well, really the only thing that I need to worry about is the current node that I'm on. I don't need to be passing through an int. I don't need to be passing through any other extra information. The only thing that I really need is the current node that I'm at. All right, so I'm just going to note that here by saying BST node. Notice I'm omitting the generics. That would have been in the question description, but I didn't want to write out a paragraph on here. BST node, and then I'm going to write current, right? Okay, cool. So then at this point I think of, okay, as I'm translating this to code, clearly I'm recursing, right? So what is probably the first thing I need to handle first? Well, I want to handle the base case, right? And what is the base case? Right, the base case is, think about me if I was calling this on a tree of this, right? This was my entire tree, just 2, right, with null children. Right, if I'm thinking about if I was finding the number of nodes in the left subtree, and I call this on the left subtree, well then I would get a null node. Right, so I need to handle that. And then I think of, well, in this scenario, how many even nodes are there in the left subtree? And the answer is 0. Right, so then I'm going to start handling my base case, right? I'm going to say if cur equals null, doing my null check first, so I don't get any null pointer exceptions. Right, and then I'm going to say if cur equals null, I'm going to say, okay, I'm going to return a 0. I'm going to return 0, because if it is, in fact, null, well, that's exactly what's going to happen, right? If the current node I'm at is null, then technically the number of even nodes in that subtree is 0. Right, so I'm going to go on. Okay, so now I've gotten that part out of the way. I know that my node, if it's made it past this point in the code, then I know that the current node is at null, and I can recurse on it normally. Right, so then I'm going to say, okay, well, I need the 3 parts of my little formula, right? I need the left, I need the right, I need the root. I'm going to do this more, I'm going to make it more, I can make it more concise, but I want to make it more obvious. That's more important, right? So I'm going to say, okay, so I'm going to have an integer left, int left equals, what does int left equal? Well, I really just want to find how many nodes are in that left subtree, right? So it's not rocket science. I'm going to call it my even helper on which node occurs left, right? Super cool. So now I have one bit of information I need, right? Now I need the other part, right? Geez, I'm really writing a slope, but I'm going to do the same thing on the other side, right? Because I need that other bit of information. Int right equals even h. I'm going to say cur dot right. Right. Notice I'm accessing those. I'm accessing these fields without a getter or a setter. Right. That would also be denoted in the instructions, but I didn't want to write a whole paragraph out. Okay. So now I have the left bit of information and I have the right bit of information. Right. Now really the only thing I need is the current node I'm at. Is that considered even? Right. So then that's a super easy if check. Right. Say if cur dot data mod by 2 equals 0. So this is the case where that node is in fact even. Then I'm going to say in that case I'm not even going to go there yet. I'm going to think of the other case too. Right? This is the case where it's not even. Right? In the case that it's not even, right, well then all I need to do is just return left and right. There's nothing else I need to do. Right, so I'm going to return left plus right. Cool. Right, and then what am I going to do in the other case? Right, I didn't leave myself a ton of room, but I can still write it in. I'm going to return left plus right plus 1. Right? And this is a 1, not a something else, right? Cool. Right, so now I have all 3 of my bits of information, right? And yeah, even if this is a massive subtree, or this is a massive tree, the recursion will handle all of it. Right? Because at the end of the day, the number of even nodes in this subtree is a subproblem of the entire tree. Right? And so those problems can recurse down until they reach their base case right here. And using these 3 bits of information, I can calculate however many even nodes are in the smaller subtrees, and that's going to propagate up through the rest of the tree. Right? Notice how I'm also traversing on both. I'm traversing on the entire tree. I'm recursing to the left and I'm recursing to the right. I'm covering all the bases in the tree. Right? So I'm going to go left initially. I'm going to go right initially. It's going to propagate through the entire tree. Cool. Then the last thing I need to do is just finish up the public method. Right? Well, that's actually the easiest part. This this helper method is going to return however many even nodes are in the entire tree. So the thing that makes the most sense is to call that, I'm going to return even h of root, right? If I call even h of root, it's going to count however many even nodes are in the entire tree, right? And that follows this formula, or this follows the formula of left, right, and the root. So let me know if you have any other questions, but really this kind of three-step process is going to help you get through those coding questions and kind of, kind of make it easier to tackle these problems, right? Instead of thinking of them as some, huge, intimidating challenge that you don't know how to handle. So let me know if there are any other questions. If not, I'm going to turn it over to Yoon for AVL rotations. And as I'm waiting for questions to come in, I know someone asked in the chat what the complexity of build heap is. Jacob answered in the chat. He said O of n. And if you want to think of a reason why it's O of n, you can basically think of how and I'm going to act like this is a min heap or a max heap. Obviously, it's not though. Is that the down heaps towards the bottom of the tree are not very costly, right? And the down heaps as you go up the tree, so the down heap here, the down heap here, the down heap here, would all be very not costly. And then as you go up the tree, they get more and more expensive, as more and more levels of the tree could be involved in that down heap operation. And then if you take the summation of all of those down heap operations, they all sum, they converge to 2n, but since big O notation, we get rid of constants, it just simplifies to O of n. So anyways, that's the story behind that. That'll be good enough for the test if it were to show up there. Anyways, if there are no other questions, I'm going to give it over to you. Thanks.
Hey, welcome back, guys. So now we'll cover AVL rotations. So just a quick review. AVL rotations are the operations that actually balance the AVLs. And just a little bit front, a little bit more. Oh, further away. Okay. And balance factor is what we're going to look at when we decide which rotation to perform. And just a quick review, balance factor is calculated, it's height of the left child minus height of the right. Okay, so I'm going to first cover the two basic AVL rotations. The first thing that I'm going to cover is the left rotation, or the right rotation, sorry. Okay, so when do we want to perform a right rotation? So we want to perform a right rotation when the unbalanced node has a balance factor equal to 2, and its left child has a balance factor of either 1 or 0. Okay, so you can imagine that I have this tree right here that's left unbalanced. And to fix this, I'm going to perform a right rotation, which will give me that. So you can see that if this tree was part of some bigger tree, right? So if X was connected to some bigger tree, then the Y becomes the new root of this subtree, and Y's right child, B, moves to become X's left child, and Z just stays the same. So that is a right rotation, and if you have a balance factor equal to 2, and its left child is a balance factor of 1 or 0, it's going to fix the tree. Okay, so that's one basic rotation, the right rotation. The next thing that I'm going to cover is the left rotation. And this is sort of the opposite case. So when do we want to perform a left rotation? So when the balance factor of the unbalanced node is equal to -2, which means that it's right unbalanced, and its right child is also right heavy. Yeah. So the right child has a balance factor of -1 or 0, and just to mention this, when you're performing the rotation, you always want to so the balance factor and height of the nodes are going to change, right? So for example, here, because height is a function of the heights of the children, because the children of the nodes have changed, the height and balance factor is also going to change. You always want to update from the bottom up. Okay, so what that means, you always want to update the nodes that end up at the bottom first. So in this case, you want to update X first because X is more towards the bottom than Y, and then Y. Because if you update Y first, then X is going to have an invalid height, and you're going to end up with an invalid height for y as well. Okay, and you don't have to update z because z's children has not changed. So going back to the left rotation, so you can also imagine that this tree is also part of a bigger tree. If you perform a left rotation on z, then what you have is this tree. So y becomes the new subtree, the new root of this subtree. Z comes down, and y's left child d becomes z's right child. Okay, so these are the basic two AVL rotations, the right rotation and the left rotation. Okay, so now I'm going to cover the more sort of complicated rotations, but they're not really complicated because they're made up of these basic rotations. So imagine you have an unbalanced subtree. Actually, yeah. Okay, so imagine you have a subtree like this. So as you can see, it's similar to the right rotation case in the sense that you have a left unbalanced node here. So you still have a balance factor that's equal to 2. Right, but you sort of have this zigzag shape in the tree. And if you were to just perform a regular right rotation on this tree, then you're not going to get, it's not going to fix the unbalancedness. Okay, so we have to do something different if we have this zigzag shape. So x's left child is going to have a balance factor of -1. Okay, and if you have a shape like this, again, if I just perform pure right rotation on x, it's not going to balance the tree. So we have to do something different. And that is a double rotation. So what we're going to do is we're going to make this subtree look like this tree because this tree we can fix. Right? So a way of doing that is to first perform a left rotation on z. And if we do that, we're going to go from this tree to this tree, which we can fix by just doing a right rotation. So this is a double rotation. So this is the left-right case. And the other sort of the opposite of that is if we sort of flip this tree and okay, so I didn't have room here, so I wrote it at the bottom. But you can see that this also has a zigzag shape, and it's similar to the left rotation case in the sense that z is right unbalanced. So it has a balance factor of 2. But its right child, unlike this case, has a balance factor of -1. Okay, and again, if you just perform a pure left rotation on this tree, it's not going to fix the tree. So what we're going to do is similar to the left-right. We're going to perform a right rotation on x first. So perform a left rotation or right rotation on the right child, which will give us, which will take from this, which will change this tree to look like this tree, which then we can fix by a left rotation on Z, the unbalanced node. So this is the right-left rotation. Okay, and just to hammer this point, you always want to update the height and balance factor from the bottom up. So in the double rotation case, you're going to be updating, so when you update or when you rotate X, you update X first because that's what ends up at the bottom, and then Y, and then Z, and then Y. Okay, so update X first, and then Y, and then update Z, and then Y again. And here you don't have to update X because X's children has not changed from this tree, going from this tree to this tree. Okay. Do you guys have any questions? All right. And we'll move on to the next topic.
All right, up next we're going to talk about some hash maps.
specifically how we probe in HashMaps. We're going to start off with linear probing, which is what you guys covered on your homework. Do keep in mind that because you covered this one on your homework, this will be the only one that you could be responsible to code for. The other ones you still be responsible to diagram, but you won't have to code it. All right? So we have a blank, empty hash map here, and let's do some operations to illustrate how we're going to do linear probing. So first off, I do want to write down just the normal, we'll call this hash. Int hash. And this is going to be the generic formula hash code mod. So this is the generic formula to calculate the initial index at which your element may be. And And this is before you actually do any probing. So it's like the first spot that you check, right? And I want to point out something very critical here, right? We're having to use an absolute value, and that's because key.hashcode is not guaranteed to be a positive number. So we must make it positive so we can index into an array. We also are modding by the table length. Now, in general, this is going to compress all of our numbers from being like, let's say, negative integer.min, or integer.min value to integer.max, right? It compresses it from that to like an index 0 through 9, right? Because our table.length is equal to 10, right? Another very important thing I want to point out here, and a couple students missed this on their homework, is that this mod is inside the math.absolute. And the reason we have this is purely to cover the integer.min value case. We've mentioned this a couple times in recitation in class, but integer.min value is slightly greater in magnitude, right, than integer.max value. Which means that if you call math.absolute on integer.min value, this will equal
Gary.
Mike. The mic.
All right, how can you guys hear me now? Might be. Okay, cool. So hopefully I'm a little bit louder now and y'all can hear me. Right, so what I'm trying to showcase here is that if I call math.absolute on integer.min value, it's going to give me back integer.min value, right? And this is still going to be a negative number, right? And that's not going to work for our hash. So we are going to mod it by the table length inside the math.absolute, because modding by, like, let's say 10 here will reduce integer.min to something we can represent with a positive number, right? That is one specific edge case that we do test for in your homework. You should also expect to, we will also expect you to handle this edge case anytime that you have to code this. Okay, so getting back to linear probing, right? This is our initial hash, right? And if we have to actually do the probing, then our current index is going to be equal to hash plus I, so this would be inside a loop, mod table dot length. And you guys should notice, I saw this on a couple homeworks, and it broke my little heart. A lot of times you guys would use the mod table dot length in your initial hash calculation. But any time that you're going to be indexing, into an array in like the HashMap sphere, you have to be modding by table.length. This is going to keep you from getting that array index out of bounds exception. It's absolutely critical. But this I here is what will change each time, right? And it's this being an I that makes this linear, all right? So let's do some operations and see what happens. So we'll do put 4. It's our first operation. And let's say that our hash code is simply going to be so I'm only going to put the key here first off, right? So our key is going to be 4, and our hash code for that key is simply going to be the number, the actual number of the key. So key.hashcode would be 4, mod table length of 10 still gives us 4, so 4 is going to go right here, right? Easy peasy lemon squeezy. We did not have a collision, we didn't have to probe. But now let's try put 14. All right, that will also map to 4, right? So key.hashcode will be 14. We'll mod that by 10, and that will get us 4, right? So that places us here. But row, we have a collision, right? There's already something in the hash map at this ideal location. So now we're going to go into our loop and investigate, using linear probing, where the correct place to place this 14 is, right? So when I is equal to 1, right, we're going to go, our initial hash was 4, plus 1 is 5, mod 10 is still going to be 5, right? And that will have us place 14 right here. So notice that there was a collision, but it was only moved 1 index over. So we only had to probe 1 time. Now let's do put 5. Right? 5, key.hashcode will be 5, mod 10 will also be 5, and that will place us here. Again, there's a collision. Let's look at our current index. Let this go to 1, right? 5 plus 1 is going to be 6. Mod the table length of 10 is still going to be 6, and that's going to have us place 5 right here. Okay? Now things are going to get interesting, right? We're going to do a remove. And we're going to remove 14, something that is in the hash map, right? So just like before, our initial hash is going to place us at 4, okay? And then we're going to start probing. And on our first probe, when I is equal to 1, right, we will find 14. So we started here, and then we'll go here, right? This is very critical. Some of you guys had struggles doing this in your homework, and it's an absolutely essential thing in probing for hash maps, right? Typically, in a data structure, when you're going to remove something, you set it to null. That does not work here, right? And we're going to show you why. We're going to do the correct thing, right? Which was we're going to flag this as deleted. So anytime you guys see a flag, that means that it's deleted, right? What this means is that the map entry is still in the backing table of the hash map. However, to the user, i.e. the person who did import java.util.hashmap, right? To them, they would not be able to find 14 in their hash map anymore. It's essentially gone to them. But this is why we have this here, right? Let's do our next call. Remove 5, right? And what's going to happen is we will map our initial hash will place us right here, right, on 5. Now I want to show you guys something. I'm going to do something incorrectly now to illustrate what would happen. And we'll go over these operations at the end to kind of bring everything together. But in remove, and in every single one of your probing operations, right, and put and remove, you're always going to have null terminate your search, right? Well, if this was null, right, then when we went to hash where we had remove of 5, so key.hashcode is 5, mod table length of 10, places us here, right? If this was null, we would assume, we'd have to know, or we would assume that 5 was not in our hash map because we investigated a spot and there was a null, which will always terminate our search, right? This is why it is absolutely essential to not set to null and instead use this deleted flag. There's really no other way to get around it because now what happens? We map to 5, right? We see that it's not there. We check again, right? We probe linearly to just go to the next index. Bada bing, bada boom, there's 5. We can set it to null, or not set it to null, set it to removed, right, and return its corresponding value. And that's how we would handle that case there. Now, let's look at the case of, we'll do one more operation on this. We'll remove 24. So 24, key.hashcode would be 24, mod table length is going to give us 4, right? So that maps to here, okay? It's not here. We then probe once. Again, because this is a deleted, right, we haven't hit a null yet, so we'll probe again. All right, and then we'll probe one more time. And now that we've hit a null, we can know for sure that 24 is not in this hash map. Because essentially what happened is, if 24 was put, let's say we did 24, like put 24, right? It would map to here, and it would have to be like along this chain, right? Let's say ideally it would be here. The next most ideal spot would be here, but if something was already there, it would go here. The next most ideal spot would be here, right? But notice that that means 24 would be placed somewhere between here and this null if it was ever put into the hash map, right? Which is why we use these deleted markers. So in the case that we get to here, we see our null, we terminate our search. This remove 24 would have us throw a no such element exception. Right? Okay, cool. So that covers most of the normal cases that have to come up with linear probing, right? It's pretty easy. It's not that big of a deal. But there's one little edge case here that a lot of people have problems with. All right. So now we're in the case where our hash map is filled entirely with deleted markers. So normally when we're doing any of these probes, like we always know that null is going to stop us, right? But let's say in this case, let's just call like a put, and we'll do 34. Put 34. So that will map us to 4 to begin with, right? Well, it's deleted. So we'll check the next index. Well, it's not 34. It's deleted. It's not null, so we have to keep probing. We keep probing. We keep probing. We keep probing. We wrap around. That's handled by this modding table.length. We keep probing. We keep probing. We keep probing. We keep probing. And notice that if you only had null be a terminating condition for your search, you would endlessly probe. This would be an endless loop, right? So what's our other stopping condition? It's if we probe table.length times. And we'll summarize, I'll summarize this for you at the end after we go over some of the other probing collision strategies, right? Okay, so at this point in time, does anybody have any questions on linear probing through with hash maps?
So is it possible to make an optimization for linear probing and terminate or remove if the index's data is equal to n but it's flat?
Okay, so there actually is, right? I was debating whether or not to go through this with you guys, but absolutely. So the question is it possible to make an optimization that essentially when you're doing like a put or remove, right? Let's say you, so here's the thing, we'll be careful on this. The question is, if I'm probing and I come across a key that matches the key that was inputted, right? Input. Is there an optimization I can have there? So one of the nice things is that if you hit that key that matches that's already been removed, right? You don't have to continue to probe to null because it's not possible for that key to be present anywhere after the matching one that you just found. Importantly though, and I saw some people do this in office hours and I wanted to be clear on it, right? Let's say we're doing like put 14, right? When we come across 14, well, so first we'll hit 4, right? And that's deleted. And then we'll come across 14, and that's deleted. So what this allows us to do is know 14 is nowhere beyond this spot in the array, right? Or in the backing table. But some people would then essentially do this. Unflag 14 and replace the value. We are not going to do this because notice that the first deleted marker you came across, hash initially placed you to 4. The first deleted marker you came across is the most ideal space to place this key. So we'll actually put 14 here. This is in the example of doing a put, right? And it won't have a flag, right? And now notice 14, the key does, like, don't confuse this with the key popping up twice in the hash map. The fact that this one is deleted, right? When we come across this key, we know that there's no other non-deleted version of that key in the hash map. So that's kind of the put example, all right? Now let's look at the remove example. So if we do again, we'll say remove 14, that will initially map us to 4, right? When we then probe and see 14 as flagged as removed, we don't have to keep probing till we hit null or we probe table.length times. Neither of those are necessary. Instead, because we've come across the key and it's already been removed, remember what we said, that guarantees that there's not another non-removed version of that key in the hash map. So in remove, we'd land here, we'd probe once, we'd see that our key matches and that it's flagged for removal, and we can immediately throw an exception, right? A no such element exception, just like we did here in 24, right? So I think, does that answer your question on the optimizations for linear probing with removed map entries? I think so. Okay, cool. So I'm going to transition this now to our other probing strategy. Again, you will not have to code this, but it is necessary that you understand how it works and you can diagram it, right? So here's the thing. You just did linear probing. Hopefully that made a good bit of sense to you. Now, quadratic probing is an extremely similar method, right? I actually joke about it being very different in my recitation to highlight how similar it is. You're literally just going to do this. Instead of it being plus I, it's going to be plus I times I, which is essentially I squared, right? But we're not going to use the math.pow function. We're going to do it like this. And we're still going to mod by table.length, right? So now we are in the world of quadratic probing. Okay, and we're going to do a lot of the same operations here to just show you the real easy difference between these things. So we'll do put 4 again, right? That'll initially map to 4. There's nothing in there, so it'll just be placed right in. Now when we do put 14, right? This is going to map us to 4. That's occupied, so now we'll let I be 1. Well, hash, which is 4, plus 1 times 1, which is 1, mod table length, so we got 4 plus 1 is equal to 5, mod 10 is equal to 5, right? So 14 is going to end up right here. Notice that your first probe in quadratic probing looks just like your first probe in linear probing, for the reason that I is both 1. Now, let's see an example where we have a slightly more complex collision. So we'll put 24, right? Again, this would, 24 modded by 10 is going to be 4, right? That'll place us here, okay? We'll let I equal to 1, which will place us here. That's where 14 just went. But Rutrow Speed Racer, that's still occupied. So now let's look at what happens when I equals 2. And I'm going to specify this out down here. So our hash is 4 plus 2 times 2 mod 10, right? This resolves to 4 plus 4, 8 mod 10, which will equal 8, right? So our probing went initial, first probe, and now second probe is 1, 2, 3, 4 spaces away from the initial index, okay? So notice that like in linear probing, 24 would have ended up here. In quadratic forming, it's thrown farther away, okay? Okay, so I now want to show you, we saw in linear probing the example where you loop forever because you have a bunch of deleted markers in your hash map, right? Well, quadratic probing presents another opportunity for infinite looping, but for a different reason, and I want to highlight this for you. So we're going to switch our example here because I know this one works for this. And we are going to have a hash map of size 6. So, with a table back of length 6, right? I didn't increment size any time during my examples. I apologize. And we're going to call these operations. So we'll first put 12, okay? 12 mod, in this case, so now table length is 6, right? 12 mod 6, put it here too, is going to be 0, right? So that will place 12 here. And notice we could place it in because 0 was a null. All right, now we'll do put 7. 7 mod 6 is 1. We can place that in because there was a null there. Now we'll do put 9. Notice none of these have actually had collisions yet. 9 mod 6 is going to be 3, so we'll put 9 right there. And we'll try put 4. 4 mod 6 is 4, so we'll place this right here. And notice we haven't had any collision yet, so it's all good. We're thinking like, oh, there's no worry in the world. But now let's check this out. We'll do put 6. Okay? 6 mod 6 is going to map to 0, right? Well, that's occupied. So now we're going to do 6 plus 1 times 1, which is 1, mod table length is 6. So 7 mod 6 is going to place us here. This is our first probe. All right? So we had first, second, right? Now we're going to look at our, well, this is our first attempt to place in, our second attempt to place in, and now we're going to let I equal 2, right? Which is going to bring us to 9. I think, actually, I'll write what I equaled under here, right? So this was I equal to 0, I equal to 1, I equal to 2, and remember that's because it's squared. Right? And then when we let I equal 3, right, that's going to wrap us all the way around to 9. Or, yeah. Yes. Okay, so notice, so our initial one, our first attempt to probe, our second attempt to probe, then wraps around to our third attempt to probe. When we try to probe again, when I equals 4, right, 4 times 4 is going to equal 16, right? Plus 6 is going to give us 22. Yep. And when we mod that by 6, we are again back at 4. So we're right back here. And if you believe me, or you can keep checking it yourself, if you let I continue, this will just keep checking these spots over and over and over again, right? And the problem now that we have is you're never going to find a place to put this key value pair, right? Because you didn't hit any deleted markers, you haven't hit null, right? And you've, like, even if you stop at probing table.length times, right? What are you going to do? Because you haven't found a place to put it. So you do stop probing after table.length probes, right? But now, because this just it doesn't have a place yet, we're going to need to resize. So stopping at table.length probes in quadratic forming, and quadratic probing, necessitates a resize. Can they see that on the screen? Okay, well, so that's what this note is here. Stopping at table.length probes in quadratic probing necessitates you resizing, right? And I'm not going to go through the effort of resizing this to just place everything like you've already seen. I think we're good on that. I just wanted to take the time to do this to show you that you will have a different condition, like it's the same stopping condition, but it has a different impact on how you handle the environment, right? Do be clear, right, that if this was deleted and we tried to put 6, then we'd probe table.length times, and we'd end up placing 6 right in here. But in the event that we don't have any deleted flags, we can do that infinite looping, right? And that's what we're trying to avoid here. So now, does anybody have any questions on quadratic probing? Does something not make sense here? I think the biggest mistake in this is really this I times I, right? So this number will be +1, +4, +9, +16, and so forth, right? It's I squared. Do we get any questions for quad probing? Cool. So I think now we're going to move on to double hashing, which is our last type of probing style collision strategy for hash maps. Okay.
Is quadratic probing better for large arrays?
So the fact that your I is going to be squared each time, I think I would say it lends itself better to larger arrays. Because you will loop back around quickly, but in a smaller. So really the thing here is this max load factor is going to probably push you towards a larger array as needed, right? Because if you start off with a really small one and you put some stuff in there and you start wrapping around in your probing, right, it's going to be very easy and quick for you to get to an extent where okay, I can only put things in 2 places. For instance, like a size 2 array, as soon as you put 2 things in there, or it's going to necessitate resize, and that will kind of continue to happen. So I think, Jacob, you can confirm this.
What are the advantages, disadvantages of each type of probing?
So quadratic probing, does it have less collisions than linear?
In general, because it's spread.
Yeah, in general, because that's kind of like the idea of a hash map, right? It's let's spread stuff out in this array. You sacrifice space, right? You have this huge array and not everything's occupied. So you're sacrificing space, but when you get these kind of a good spread between elements and clusters, then you're going to very quickly be able to put things or find that you find the thing you're looking to remove or the fact that it's not there very quickly, right? So quadratic probing is going to be quicker than linear probing, right? As far as this one, double hashing, I'm not. Yeah, is it? I'm not sure if that's.
I'm going to give my answer for this one. So the basic idea is, since quadratic probing kind of spreads out your data better, if you're dealing with hashes that are kind of grouped up or close to each other, that will give you a lot of collisions with linear probing, but quadratic probing will spread them out a little bit better. But for double hashing, so if you're dealing with a bunch of hashes that are exactly the same, for the sake, we can talk about ones that are exactly the same. Quadratic probing will still have just as many collisions versus double hashing. If your second hash function gives you a different value for objects that maybe give you the same value for your first hash function, it kind of depends on what that second hash function is. Then you can potentially get even elements that have similar hash codes to be spread out or go in different places, which is an advantage of double hashing over the others. But double hashing and quadratic probing and, as you'll see, as we'll mention, double hashing can both run into that infinite probing situation where linear probing can never have something like that. So you might have to do more resizes with quadratic probing and double hashing, whereas you wouldn't with linear probing.
So linear probing will not necessitate you to resize when you probe table times, but you still can run into the infinite loop due to having removed flags, right? If you don't have a null, then you will run into that problem.
It won't be an infinite loop. You'll just go through everything and determine that there is no null spot, and you have a remove marker. Versus with a quadratic probing or double hashing, you won't find a null spot that might exist.
Okay, I see what you're saying. Okay, cool. So, as some of you may be questioning now, Jacob was talking about a second hashing function. Right? So as normal, we have our hash that we've been using the entire time. It's just key.hashcode mod table length. Right? And now we're also going to have another integer. We'll just call it d in this case for our double hash. And it's going to be defined, and this formula would be given to you. Right? We're taking some prime number that is less than the length of the array, and we are subtracting from it. Key.hashcode2. Notice this. This is not the same hash code, right? This is a different hash code function, right? And then we're modding it by 7. And what this guarantees us is we have 7 minus something modded by 7. So this number in here will never be 7, so we are guaranteed a positive number, right? Strictly positive, meaning 0 is not included, right? So how, when we calculate our current index, it's going to be a little something like this. It is our initial hash plus d times I mod table.length. Right, so previously, like linear probing, this is just I. Quadratic probing, it's I times I. And then in double hashing, we're using a different hash function to generate an integer d, right? And then we use this as kind of like an attachment to our probing, right? And let's look at a lot of the same operations we just did, but now with this kind of collision resolution strategy. So we put 4, that will map to 4. We put 14, and let's check this out. This one's kind of interesting, right? So in both linear and quadratic probing, 14 would have gone here, right? But let's do a little bit of maths and see what happens, right? So our initial hash is going to be 4, right? So for our current index, we're looking at 4 plus d is going to be what? D is 7 minus key.hashcode 2, which, so we just have them be the same thing? Yeah, I think we can. So in this case, we'll just say that this also returns the key value, right? So this will be 7 minus 14 mod 7, which is what? 14 mod 7 is going to be 0. So this is going to be plus 7 and then times I, which in this case is 1, right? And then mod, do 1 here, table.length. This will give us 4 plus 7 is 11, mod table length, which is 10, will give us 1, right? So 14, instead of being mapped here, like it would have in linear or quadratic probing, the first probe maps us all the way over here, right? And we now have a big spread. Notice that the initial collision is now very far, like this was our initial collision, and where we placed our data is pretty far from this initial collision, especially considering the alternative probing methods, right? So there was put on 14, which put it in a very different spot, and let's do put 24, right? Again, this is going to get mapped initially to 4. We'll see that it's full. And now let's calculate d. So we have 24 plus d, which in this case is going to be 24 mod 7, which comes out to 3. So 7 minus 3 is going to be 4 times I in this case is 1. Right? And then we're going to mod this by our table length, which is 10. So 24 plus 4 is 28. Mod 10 is going to be 8, right? So initially we tried to place 24 here. Our double hashing function resolved our collision in one step, and we put it all the way there. Okay, so now we're going to do a very simple case to just show you what happens when you try to remove something that's not in the hash map. You know, it will terminate like you expect. So we'll remove 34, right? That'll initially map to 4, which will necessitate us to continue to probe, right? In this case, we're now going to have 34 plus 34 mod 7 is 6. So 7 minus 6 is 1, right? And we're going to multiply this by I. We'll mod this whole thing by 10. And we'll end up with 34 plus 1, 35 mod 10, which is 5. Oh. I think something went wrong. What's 34 mod 7, guys?
6.
7 minus 6 is 1. Okay. All right, cool. So I think I just wrote it down. So we initially will check here. Our double hashing will have us end up here. We'll see that 34 is not in the hash map because we hit a null, right? And this can allow us to throw an exception, right? So pretty clearly, I think we've gone through the 3 different types of probing methods that we have in hash maps, right? And we see that essentially the same thing's going on in all of them, where we have this initial hash plus something, where this is what changes. Right? That's kind of our juicy little part that changes. And we're always going to be modding by table.length. Right? You've now seen the 3 different examples with very similar methods or method calls, right, to show you how it's a little bit different. Now, I'll give you guys a chance to ask any questions about this hashing, the double hashing on a conceptual level. And if you guys are good, I want to move on to HashMap operations and kind of like things you need to check for in put, in remove, and in resize backing table, because there were a lot of problems with these methods in the homework. And we want to clarify some things.
Someone did ask if we could go over external chaining.
Okay, so yeah, we can go over external chaining. I think I can do that really quickly. So external chaining is cool in the sense that if you learn linear probing, right, or especially if you coded linear probing, then external chaining makes a tremendous amount of sense to you. And we're going to move this guy a little bit. Right, and this is no longer probing. Right, we're doing external chaining. Right, and here's something that is very, very nice about external chaining. Right, it is a closed addressing strategy, or collision resolution strategies. Right, and what that means is that, you know, like in all of the other probings, right, I would initially check here, right, and let's say 4 was there, right, and if I was to do something like 14, right, 14 could end up here, but because it's not there, it ends up here, or because there's something there, it ends up there, right, and that means that 14 isn't necessarily at this first address that we calculate, which is calculated exactly, let's put this lower. Exactly the same as it's always been. Math.absolute key.hashcode and then mod table.length. Right? So 14 might not end up in this initial spot. With external chaining, closed addressing means that you are guaranteed to put or to have your data in the index that you initially calculate, right? So then you must ask, like, well, how do you put 2 things in that index then, right? Because if 4 and 14 are both guaranteed to be in index 4, how can I have 2 data elements occupying the same space in an array, which is the backing structure of this hash map? Well, quite easily, you just have a linked list, right? And that's what essentially your external chain is. Now, Jacob, real quick question. When they add to the external chain, do they add to the front or the back? Okay, so, okay, cool. So let's look at some methods here. So we'll put 4, right? 4 will get mapped here. We'll put 14, right? And what will happen is, so instead of this just being placed in there, you essentially have like a linked list. Not essentially. You do have a linked list with the head of each of these in the index of the array. So when we go to 4, what we'll have to do is check through this linked list. So 14 is not in here yet. We'll check through this linked list, go through it and see like, hey, is this already in here? If not, we're going to add our new node, it's a little big, with 14. Okay? Now let's do like put 24. We'll come to here. We'll check the head. Nope, that's not 24. We'll check 14. Nope, that's not 24. We can add this. If I was to do put 14 again, right, I would come here. And this is why you have to check, right? Because if you just added this on to the end of your linked list, kind of blindly, you'd get that, right? Where we have duplicate keys in the hash map. You cannot have this, right? So I would have to check the head of the linked list and then search through it until I found 14. I would find 14. I would then replace its value, return the old value, and I'm good to go. So external chaining is very, very easy in the sense that you're really just like putting linked lists in these things, and as long as you remember to search through them to ensure that you don't get any duplicate keys, it's almost, you know, blindly intuitive to just say like, all right, cool, I'll just add it to a linked list in this spot. The one interesting thing is, I don't think you guys, I mean, you won't have to code this, but just for your reference, right? When you resize these things, we'll just have this as deleted for right now. When you resize these things, you will go through each index in your table, and at each index, you will go down all the linked lists. Right? So at index 0, if this isn't flagged, I'll put it in my new one. If this isn't flagged, I'll put it in my resize. If this isn't, and so forth. If these are flagged, right, then it doesn't go in. Okay? But here's a curious conundrum. If you place this exact node into your new table, right, it'll still have connected this. So like X and Y will be connected if I simply just copy the node over. The easiest way to fix this is you'll start at 0, or you'll start at your index in the table. You'll go through each node in your linked list, and when I get to X and I see that it's not deleted, I'll probably just make like a new node that has the same key and value, but no references, right? And then put that in my new backing table. Several times I've seen students who actually have to code this. They will like get to X and they'll realize that if they placed it in the new table with this, with Y still attached, that it'll mess it up. So their solution is we'll just set X's next reference to null. That would therefore have you lose Y and not be able to put it into your hash map. So really the best way to do it is to just grab the key, grab the value, make a new node, and throw that into the appropriate spot. Now that we've seen this, I know it's kind of quick. Do we feel better on external chaining? Do you think you could diagram it? What do we get? I think we're good? Cool, cool. So now let's transition from actually looking at diagramming all of these probing strategies to doing a little bit of overview on the HashMap operations in the probing sphere, right? So we're doing HashMap operations, and these are for probing, right? So these are the ones that you coded, like for linear probing, okay? And we have 3 real methods that we're going to investigate here. The first one is put, right? And there's a couple things that I want you guys to do in put, right? Right away, always, the first thing we're going to do is check size plus 1 and compare it with loading factor. I'm going to abbreviate load factor LF, right? Notice that this is size plus 1, right? Also notice that this must be cast to a double. Right? And the reason being is this is an integer, and max load factor is a double. So if you, so it's size plus 1 divided by table.length. And we'll compare this to max load factor. Right? We're looking at size plus 1 because we're looking ahead. We never want to exceed the max load factor. This is essentially telling us the percentage at which the table is full, but it must be a double for us to actually get a percentage. Otherwise, this will really only be like whole numbers, right? So most of the time you'll do this and it'll be 0. You won't actually hit your max load factor when you want to, okay? The second thing I want to make sure you guys are doing when you're doing your put method is to save the first deleted marker you come across. Right? Now, I say save the first one and only the first one. So you'll probably have to have some kind of Boolean flag in your code or something to like illustrate to you that you're only grabbing the first one, right? Do keep in mind that you continue probing. Many times I saw students find this first deleted marker and assume that they can just place the map entry there. You can't do that because, and we saw several examples, please rewind to look at the linear probing for put, right? There was the example where 5 was in, it was kind of like this. I'll just draw a section. Right, so we had 4, we had 14, which had been removed, and we had 5, right? And these were indexes 4, 5, and 6 respectively, right? So if we did put 5, and we got to this deleted marker and thought we could just throw 5 in here, we would end up with this, right? And this is a no bueno. We have matching keys, or we have duplicate keys in the hash map. This is why we must continue probing, okay? The next thing that I want you guys to do is, so this, and to be clear, like this is in your loop. This will also be in your loop, right? And we're going to check for matching keys. And when we find a matching key, one of two things will happen. Option 1, the map entry is not deleted. In this case, we should replace value and return old value. Notice that I did not increment size, right? That is not going to happen. And the reason that's not going to happen is because the map entry hasn't been deleted. You're just switching a value. There's not another new map entry in the backing table, right? So we have to make sure that we're not incrementing size here. That's another common mistake I saw. If map entry is deleted, very commonly I'd see students then think like, okay, cool, I can put the value in here, right? And then I can flip the deleted flag. No. You're always going to want to put your map entry in either the null spot you hit, if that's the first thing that you hit, or the first deleted marker. Because this will be closer to the ideal index, right, that you were trying to get to, rather than like this one, this map entry that has a matching key that's deleted, which could be very, very far away, right? So in this case, we're going to stop probing, place in first deleted marker, right? And it's possible that this is the first deleted marker, but it's not guaranteed, so you need to place it in there. And finally, we talked about this before. These are your loop conditions, right? We are going to probe until null, which always terminates our search, or table.length times. And this is a general put that's the idea for all of the put strategies, or all of the probing collision strategies we have. We're really focusing in on the linear for you guys because that's the only one that you can be expected to code, but it's the same basic thing with very light modifications to the double hashing and the quadratic probing. And I showed you an example of why we need to stop at this table.length times in every single one of those collision strategies we had. Okay, cool. So that's what we want to do for put. All right. Please, take a screenshot of this if you need to. I'll take one quick second before I erase it. Cool. And oh yeah, you guys can't pause it. Technology, man, blows my mind. Okay, cool. Now let's look at resize. Right? And I'm going to do resize next because it's kind of similar to put. And by similar, I mean it's pretty much the same exact thing, except for one very key difference, or for several key differences, sorry. We are only copying over non-deleted map entries. A very common mistake I saw on homework was kind of just copying over any map entry you came across. That is no bueno. If it's deleted, we do not want it in our resized hash map, right? The other thing you're going to do is we don't have to check for del markers or matching keys in the new table, which essentially just means probe until null, until you hit null, right? And the reason being is that this new table that we're populating, right, we're deciding not to put any deleted map entries in there. So we shouldn't come across any of these. And because we're calling resize on a hash map that is already a valid hash map, right, we shouldn't have any matching keys. So we don't have to worry about this at all. Okay, and then finally, and this is really big, a couple people missed this, do not use put. And the main reason being that resize allows table to shrink, which you could almost think of, I think, if you're trying to look for a reason as to why you want this. Let's say maybe you need to like condense data and you don't want to have an array that's that big, right? So resize allows a table to shrink even if it breaks max load factor. And due to this case, in this case alone, we are not going to, like, you cannot use put, or you could infinitely loop again, right? So, in the words of Forrest Gump, that's all I got to say about that on resize. I do want to go over remove with you. I'm sure you guys can have paused this by now and gotten what you needed. So let's keep on keeping on to our final operation that I want to go over with you, and that would be remove. Right? In remove, we are going to, the biggest thing we're going to have to do is in our loop, we're going to, I want a better marker. Hold on. We're going to check for matching keys. Right? And if the matching key is with a deleted map entry, we can instantly throw an exception. So if we're looping through and we find a matching key, but it's been deleted, then we're going to immediately throw an exception and we're not going to keep looping. To do so would be inefficient. If it's not a deleted map entry, then we are going to decrement size. Let's do it this way. Size minus minus, right? We're going to set removed. Right, and this is not setting to null. This is setting to remove. This is very important. We went over why we have to do this. And we're going to return the value. And it is the value that is actually in this map entry. Sometimes people, well, in this case, I think that's the only one you'd have. So there you go. You return the value, and this handles what you need to do in remove. Again, the only other thing you have to do, this would be outside of your loop, so these are loop conditions, is to probe until null or table.length times. And in the event that this has happened, right, like you go through your loop, you never come across this case, you're going to throw that exception again. Because in put, right, if you get through this condition, it means that now you're ready to put something in because you did not find it in the hash map. In remove, this means again that hitting this condition means that you haven't found it in the hash map, and in that case, for remove, right, we handle that by throwing an exception, specifically a no such element exception. Okay, so I hope that outlined the hash map operations for you a little bit more clearly. A lot of these things were missing on people's homeworks or they were having trouble with in office hours. At this point, before I toss it over to Jacob, does anybody have any remaining hash map style questions? Good. The little delay is hysterical. That little, I guess. All right, so I think we're good, and we will be right back after this commercial break. And enjoy yourself.
Hello everyone, it's me again, and we're going to talk about LSD Radix sort. That's how I choose to pronounce it. If you're exceptionally cool, you can go with LSD Radix sort, but I'm going to be using Radix sort for the... only works for integer numbers. So the first thing we're going to do is sort by our least significant digit, which is the ones place. Then we're going to sort by the next least significant digit.
Go back to 30 seconds. The audio came back. Start. Go back to 30 seconds.
Okay, I'm just going to start over because Landon telling me that things are going horribly wrong. Again, not my fault. I'm not the one running the stream right now. So we're going to talk about LSD Radix sort. Again, if you're really cool, you can go with Radix sort, but I'm going to use Radix sort because I'm not cool. So the basic idea behind LSD Radix sort is we're going to repeatedly sort by each digit of our numbers. LSD Radix sort only works for a bunch of numbers. So first we're going to sort by our least significant digit, that's the ones place, then the next least significant, tens place, so on and so forth. And the big thing that we're going to keep in mind here is all of these sorts need to be stable. And as you mentioned earlier, when we sort in a stable way, every new sort preserves the order of elements previously in the different ways that we sorted. So if numbers have the same tens place, they'll be sorted by their ones place, which is what we expect numbers to be sorted by. The number of times total you need to perform radix sort is the number of digits in your largest magnitude number. So in this case, we have positive numbers. We just can look at our largest numbers, which have 3 digits. You'll also notice that I have a duplicate data here. That's just going to show off another way of how stable radix sort is, but everything throughout this sort is stable. Here we have our buckets. This is how we're going to actually perform LSD radix sort. Basically, we're just going to alternate between taking our elements from the array, placing them in the bucket, and then taking them out of the bucket and back into the array. I'm going to maintain this original array here the whole time, but you would be actually modifying your original array when you're performing radix sort. So our first step is to go through our array and put each element in the bucket from left to right. Every bucket is a queue of numbers, so the same order we put things in is going to be the order we get things out. So 734 has a 4 in the ones place. 12 is a 2. 4 has a 4, so we put it after 734. 332, 768, 68. Sorry, I missed our duplicate. So we have this other 734, then 68, then 36. So now that we've put our elements in our buckets, we're going to do the second half of radix sort, which is actually emptying our buckets. So that means we're just going to go through each bucket one by one, starting with the 0 bucket, going all the way to the 9 bucket, taking each element and putting it into our array. So first we empty our 2 bucket. That means we have 12 first, then 332, again maintaining that order. As we take elements out, we can remove them. Then we have 734, 4, and our duplicate 734. 5 buckets empty. The 6 bucket only has 36 in it. 7 buckets empty. 8 bucket has 768 and 68. And nothing on 9. So we've completed our first iteration of LSD radix sort, and you can see our elements are now sorted by that first digit. Obviously, we're not done. We need to do 3 total iterations. So we're going to do the exact same process again, but using the second digit of all our numbers. Second being second from the right, that's our tens digit. So 12 has a 1 in the tens digits place, so it's going to go in the 1 bucket. 332 has a 3. 734 is also a 3. Maintaining that order. 4 has nothing there. That's considered a 0. We already know where this element's going to go. 36 has a 3. 768 is going to go in our 6 bucket. And then finally 68. And now we empty our buckets the exact same way we did last iteration. So we start with our 0 bucket, then our 1 bucket, then our 3 bucket. So that means we put 332, then 734, our duplicate 734, and then 36. You'll notice these elements that had the same tens digit are now sorted by their ones digit within this grouping. So here with all of these numbers, we have 2, 4, and then 6 as our ones digits. Nothing on 5, so we go to our 6 bucket, empty 768, then 68, and nothing on 7, 8, or 9. So we've now completed our second iteration of LSD Radix sort. Again, our array isn't sorted, and it at this point doesn't even particularly look close to getting sorted, but just one more iteration and we will fix everything. So now we're putting our elements into buckets by their hundreds digit. So 4 and 12 have no hundreds digit, so they go in the 0 bucket. 332 has a 3. Our 734 and duplicate. 36 also goes in our 0 bucket. Then 768 in here. And 68 in the 0 bucket. So you'll see if you're diagramming LSD Radix sort as you get closer to the end of your the last iterations of your sort, a lot of things will end up in the 0 bucket, but that's perfectly okay. Now we empty our buckets, we get 4, 12, 36, 68. Nothing on 1, nothing on 2. 3 has 332. Nothing on 4, 5, or 6. And then 7 has 734. 734 duplicate. And our 768. Nothing on 8 or 9. And thus we are done. And we have successfully sorted our array. Not only correctly getting the order of these numbers, but you'll see that these two duplicates are in the same relative order that they were in our original array. And that's because LSD Radix sort is a stable sort. In terms of time efficiency, we can't just use like end to explain the time efficiency of LSD Radix sort, because we have the number of iterations we're performing is dependent on the numbers we're actually sorting. So we give that our time complexity of radix sort is actually O of kn, and in this case k is the number of digits, like the largest number of digits that we have to deal with. So if we're sorting a bunch of relatively small numbers, think like 3, 4, 5 digit numbers, then O of kn is actually pretty good. If we're sorting huge numbers like 100-digit numbers, then it isn't great. Now in terms of like more implementation specific things, you're probably wondering, okay, how do I actually figure out what these digits are? Because if you've looked at your homework, you'll see that a lot of functions in the math library aren't actually available to you. So we're going to talk about how you actually do that calculation. Well, it's actually relatively simple. I'm going to go ahead and erase this because I won't be using the buckets anymore. So if we want to find the ith digit of a number, note that 0th digit is the ones place. We're going to take that number we're going to divide it by 10 raised to the ith power, and then we're going to take that quantity and mod it by 10. But something else you'll notice in your homework is this power thing isn't really something you can do. Java doesn't have a basic operation for it, and you're not allowed to use it in the math library. So how do we actually get this number? Well, you could have a loop to calculate it every time, but that seems really inefficient, mostly because it is. So how we're actually going to do it is we're going to first recognize the fact that on the very first iteration, we need 10 to the 0. On our second iteration, we need 10 to the 1. On our third iteration, we need 10 squared, etc., etc., etc. So if we have our main loop here, with all of our radix sort code. So here we have filling the buckets, here we have emptying the buckets. Then outside the loop, we can declare a variable called div, have it set equal to 1, which is the first value we're going to use. And at the bottom of our loop, before we loop back around,
Someone said Matthew said video down, so I'm going to transfer it.
you can see if it works.
You're on right.
Yeah,
And then
that's good enough.
change 9 and 8, change it when it's still
Yeah, just hit. I'm good.
the music. Let's get
I'm on. All right. Sorry about that minor technical issue. Again, definitely not my fault because I'm not running the stream right now. So at the bottom of this loop, again, I'll just go back. We declared this div variable at the very beginning to be 1 before we started. Then in our loop, we can use this variable here. So instead of 10 to the I, this can be just replaced by div. And that means at the end of this loop, we have to update div by doing div equals div times 10. So that means on our second loop, this will be 10. On our third loop, this will be 100, so on and so forth. One of the things I want to definitely stress about the difference between kind of how I'm explaining it here and how you're doing it on your homework is your homework, you can be using negative numbers in your array, versus here in most examples, we tend to use positive numbers because it takes up a lot less board space. In negative numbers, you need to keep in mind that the longest number, so when I say the largest number of digits, I specifically didn't say largest number, because when you're dealing with negative numbers, the largest number of digits might not be on your largest number. Imagine if you have a bunch of numbers between like 0 and 10 and then negative 5,000. Negative 5,000 is your longest number. So you're going to need to find what the largest absolute value is out of your numbers. And on your homework, you are allowed to do a pass through your number, pass through your array in order to actually figure out what that number is. Something to keep in mind is, just like when we talked about hash maps, you do have an edge case with integer.min value. Integer.min value is a very large and long number. However, taking the absolute value of it will still be negative, and thus it will be less than everything else in the array. That is something you'll have to explicitly edge case for LSD Radix sort. There isn't a nice way to handle it like there is in hash maps. So once you've found that largest number, in order to calculate how many digits it has, I'm going to erase this calculation here, is relatively straightforward. You can just set a variable equal to 0. We'll assume that num contains what your largest magnitude number is. And then while num is not equal to 0, you can increment count and do num equals num divided by 10. And that will figure out how many digits you have. So for example, 12, you would divide by 10 once and get 2, divide by 10 a second time and get 0, and that means you have 2 digits, and this loop will run twice to reflect that. So that's a nice way of figuring out how many digits you have. Keep in mind that you'll only want to run this for your longest number, because if you run this for every single number in your array, that O of n loop becomes an O of kn loop, and it's not really efficient to have an extra O of kn loop when it's not necessary. I believe I've covered most of the cases for LSD Radix sort. I've covered the efficiency, covered how you do the calculation of the digits, how you figure out what your largest digit is, and the process of placing the elements in and out of the bucket. Oh, yes. So I had 10 buckets on the board for positive numbers. I was getting to this, and I think I got interrupted by the video failure. With negative buckets, or with negative numbers in your array, you'll need a total of 19 buckets to hold all the numbers. So that digit calculation I did earlier. I'll rewrite it. It was num divided by 10 to the I, which we actually had a different variable for. Mod 10. That gives you what your actual digit number is. In order to figure out what bucket number is, you're just going to add 9 to this value to offset the negative number. So that means -9, the -9 digit. Something that has a -9 as its digit will go in the 0th bucket, and something that has a 9 in the digit will go in the 18th bucket, which is the last bucket. Now I believe I basically covered everything, so if there are any questions, feel free to ask in chat, and I'll stand here awkwardly while stream delay catches up. All right, I don't think we've got any questions, so I think now we will go to a break, and I think after that we will be ending our stream off because we're nearing the end of our time slot. So we'll be right back. Hey everyone, thank you for tuning in live and or watching this on YouTube after the fact sometime on Sunday when you're studying for the exam or Monday night when you're cramming for the exam. Hopefully all of our antics and explanations were very useful to you. Thank you all for submitting the form, sending a bunch of questions for us to answer. I know we couldn't necessarily get to everything because we got some very vague questions that were kind of hard to condense into this recitation, but we did our best to cover as much as we could. Again, if you have more stuff, we will have office hours on Monday that I'm sure will be very crowded with all of your questions, but feel free to ask us any questions on the comments of this video. I will try to look at them. This stream VOD should be uploaded relatively soon. I'll try to release a list of all the questions we covered so you can view them by their timestamp. But thank you so much.
Jacob.
This was a lot of work.
What's another great place to ask questions?
A wonderful place to ask people questions is on piazza.com. I am active on Piazza, if you haven't noticed by all the questions I've answered. Landon's also very active on Piazza. All the TAs are active on Piazza to some extent. But there's a lot of ways to ask us questions, and we'll do our best to answer them. So, with that,
Live from Atlanta, it's Friday night.
Yep. Garrett's been wanting to say that the entire time.
Bye, YouTube.
All right. Bye everyone.
Bye.